Welcome to this problem walkthrough. Today, we will explore the problem number 774, minimize max distance to gas station. This is an exciting optimization problem that challenges us to minimize the maximum distance between gas stations while adhering to specific constraints. We'll break it down step by step, discuss different approaches, and analyze their complexities. Let's dive in. In this problem, we are given an array called stations, which contains the positions of existing gas stations along a highway. These positions are listed in increasing order. Additionally, there is an integer k, which represents the maximum number of new gas stations we are allowed to install. Our objective is to determine the smallest possible value of the maximum distance between any two adjacent gas stations after adding up to k new stations. The result must be accurate to within a margin of 10⁻⁶, and if there are multiple valid answers, we can return any one of them. For the input, the array stations has a size between 1 and 50, and each position is a non-negative integer bounded by 10 to the power of 9. The value of k can go up to 10,000. The output will be a floating point number representing the minimized maximum distance, computed to 6 decimal places of precision. Let's look at an example. Suppose the input stations is 1, 5, 10, and k is 2. Initially, the distances between adjacent gas stations are 4 between positions 1 and 5 between positions 5 and 10. To minimize the maximum distance, we can add 2 gas stations. One possible solution is to place a new station at position 3, which splits the interval 1, 5 into 2 smaller intervals, 1, 3, and 3, 5. This reduces the maximum distance within this interval to 2. Adding another station will further minimize the maximum distance. The second additional gas station can be placed at position 7.5, which splits the interval 5, 10 into 5, 7.5, and 7.5, 10. At this point, the maximum distance between any two adjacent stations is reduced to 2.5. So, the output for this example is 2.500000. This demonstrates how placing the additional stations optimally can significantly reduce the largest gap between stations. Now consider a second example where stations is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and k is 9. Here, the initial spacing between adjacent stations is already uniform, with each pair separated by a distance of 1. By adding 9 additional stations, we can reduce the maximum spacing to 0.5. This can be achieved by placing one new station in the middle of each existing interval. Since the stations were already evenly spaced, this ensures that the maximum distance between any two adjacent stations is minimized to 0.500000. In a third example, suppose the input stations is 10, 19, 25, 35, and k is 3. The initial distances between adjacent stations are 9, 6, and 10. To minimize the maximum distance, we can add 3 additional stations. For instance, placing a station at position 14.5 splits the interval 10, 19 into 10, 14.5, and 14.5, 19. Similarly, placing a station at 22.5 splits 19, 25, and placing another at 30 splits 25, 35. This results in a maximum distance of 5.0 between adjacent stations, and the output is 5.000000. Finally, let's review some edge cases. If there is only one station, for example stations equals 0 and k equals 1, we can place one additional station anywhere, as there's no existing gap to manage. When there are large gaps, such as stations equals 1 billion, with k equals 100, additional stations must be placed strategically to reduce the largest interval. In cases where the stations are already evenly spaced, like stations equals 1, 2, 3, 4, 5, with k equals 10, the solution involves placing stations within existing intervals to further reduce the maximum distance. For very large values of k, such as stations equals 100, with k equals 10,000, the maximum distance can be reduced to a very small value. Finally, when intervals are non-uniform, like stations equals 1, 5, 10, 20, with k equals 5, the largest gaps should be prioritized for adding stations. These scenarios help illustrate the diverse considerations required to solve the problem optimally. To solve this problem, we first considered a brute force approach. The idea here is to simulate every possible placement of the additional gas stations, compute the maximum distance between adjacent stations for each configuration, and then minimize this maximum distance. While this might seem straightforward, it quickly becomes impractical because the number of possible placements grows exponentially. Specifically, for n existing stations and k additional ones, there are O, open parenthesis and plus k close parenthesis to the power of k, combinations. This kind of complexity is infeasible for competitive programming scenarios or large inputs, where efficiency is critical. Instead, a more refined method involves binary search on the maximum distance. Here, the focus shifts from explicit placements to finding the smallest maximum distance that can be achieved with k additional stations. By defining this as a binary search problem, we iteratively narrow down the range of possible values for the maximum distance. For each candidate distance, we calculate whether it's possible to place the stations such that no two adjacent stations are farther apart than this distance. If it's feasible, we try a smaller distance; if not, we increase it. This method is much more efficient, with a time complexity of O, n asterisk log, max_distance, where we perform binary search and, for each midpoint, compute the required number of stations in linear time. An alternative approach is to use a priority queue, or max heap, in a greedy manner. In this method, we focus on the largest gaps between existing stations, iteratively splitting these gaps by placing new stations until all k additional stations are used. The largest gap is always prioritized, and the heap structure allows us to efficiently track and update these gaps as new stations are added. While this approach is intuitive and directly addresses the largest gaps first, it has some drawbacks. The implementation is more complex compared to binary search, and it is less efficient due to the logarithmic overhead of maintaining the heap. Specifically, the complexity for this approach is O, k log n, which involves logarithmic updates for each of the k placements. Ultimately, the binary search approach is preferred for this problem. It is more efficient, with a complexity of O, n log, max_distance, and easier to implement. The binary search method also leverages the monotonic nature of the problem, where smaller maximum distances require more stations, ensuring a clear and systematic strategy. Another significant advantage is that it guarantees an optimal solution while still being computationally efficient. The greedy priority queue approach, while valid, is less practical for large-scale inputs. The crux of this problem lies in reformulating it as a decision problem. Specifically, we ask, is it possible to place k stations such that the maximum distance between any two adjacent stations is less than or equal to d? This reframing is what makes the binary search approach both efficient and feasible. The key insight here is that for a given maximum distance, the number of additional stations needed can be calculated in O, n, time using a simple greedy method. This insight dramatically reduces the computational burden compared to brute force methods and makes the binary search strategy scalable. The aha moment comes from realizing that the problem's monotonic nature, where smaller maximum distances require more stations, allows us to systematically narrow down the range of possible solutions. By combining the decision problem formulation with binary search, we arrive at an approach that is efficient, straightforward to implement, and guarantees correctness. This final strategy avoids the pitfalls of brute force, outperforms the greedy priority queue approach in scalability, and provides the optimal solution within the given constraints. To tackle this problem, the goal is to minimize the maximum distance between adjacent gas stations after adding k new ones to a highway. The highway is represented as a sorted list of positions where existing gas stations are located. We approach this using binary search on the answer. First, we define the search space. The maximum distance right now is the largest gap between any two consecutive gas stations, referred to as max_gap. On the other hand, the minimum distance, min_gap, is 0, since we can hypothetically make the distance as small as possible. Our task is to find the smallest possible maximum distance, d, within this range. Binary search is then applied to this range. For each midpoint d in the search space, we simulate whether it's feasible to achieve this maximum distance by placing k or fewer additional gas stations. The simulation function plays a critical role here. It takes the proposed maximum distance d as input and outputs a boolean indicating whether this distance is achievable with the given k stations. The logic involves initializing a counter, stations_needed, at 0. Then, for each gap between consecutive stations, we calculate how many additional stations would be required to ensure that no segment of the gap exceeds the proposed distance d. This is done using the formula stations_needed plus equals gap // d, which performs integer division. If at any point stations_needed exceeds k, we return false immediately. Otherwise, if the loop completes and stations_needed stays within the limit of k, we return true. Based on the result of this simulation, the binary search updates its range. If d is achievable, we shrink the range by updating max_gap to d, aiming for smaller distances. Otherwise, we increase the range by updating min_gap to d, allowing for larger distances. Binary search stops when the min_gap and max_gap values converge. At this point, the algorithm returns the converged value as the result, which is the smallest possible maximum distance. This approach, known as binary search on the answer, works effectively because we're minimizing a continuous value, d, which makes it well-suited for binary search. The simulation step employs a greedy strategy, adding stations in a way that maximizes coverage and minimizes the number of stations used. Looking at the complexity, binary search runs 4 log max_gap iterations. Each simulation involves checking all n1 gaps, which takes n computations. This leads to a total time complexity of n*log max_gap. To implement this algorithm, we rely on a few key data structures. First, the input positions of existing gas stations are stored in a sorted list. This allows for easy computation of gaps between consecutive stations. Additionally, simple variables like stations_needed and gap are used to keep track of intermediate states during the simulation process. Let's now illustrate this with an example. Suppose the input positions of gas stations are 1, 5, 10, and we are allowed to add k equals 1 new station. The task is to minimize the maximum distance between adjacent gas stations. The initial gaps between consecutive stations are 4, 5. The binary search starts with min_gap equals 0 and max_gap equals 5, the largest initial gap. First, we test the midpoint d equals 2.5. To simulate, the gap 4 requires seal, for /2.5, 1 equals 1 station, and the gap 5 requires seal, 5/2.5, 1 equals 1 station. This totals 2 stations, which exceeds k. So, we update min_gap to 2.5. Next, we try d equals 3.75. Again, each gap requires 1 station, totaling 2, which is still more than k. We update min_gap to 3.75. Finally, we test d equals 4.5. For the gap 4, no extra station is needed, and for the gap 5, 1 station is required. This totals 1 station, which fits within k. Since d equals 4.5 is achievable, we update max_gap to 4.5. The binary search converges when min_gap and max_gap meet, resulting in d equals 4. This value represents the smallest possible maximum distance between adjacent gas stations after adding the new station. The output for this example is 4. This solution implements a binary search approach to solve the problem of minimizing the maximum distance between adjacent gas stations after adding k new stations. The method minmaxGasDist takes a sorted list of station positions and an integer k representing the number of additional stations to place. First, a helper function can_place_stations is defined. This function checks if it's feasible to place the additional k stations such that the maximum distance between any two adjacent stations does not exceed a given value max_dist. It iterates over all station gaps, calculating the number of stations required to split each gap into segments of length at most max_dist. If the total required stations exceed k, the function returns false, otherwise, it returns true. The binary search is performed over the range, left, right, where left starts at 0 and right is the largest gap between the first and last stations. The precision threshold epsilon is set to 1e6 to ensure the result is accurate to 6 decimal places. Within the binary search loop, the midpoint mid of the current range is calculated. If it is feasible to achieve a maximum distance of mid, using can_place_stations, the search narrows to the left half by setting right equals mid. Otherwise, the search narrows to the right half by setting left equals mid. The loop continues until the range is smaller than epsilon, at which point left is returned as the minimum possible maximum distance. This approach ensures an efficient solution with logarithmic complexity in the binary search and linear complexity for the feasibility check, resulting in an overall time complexity of O, n asterisk log, d, where n is the number of stations and d is the range of the search space. Here, we begin our Java implementation by importing the necessary utilities and defining a class called solution. The core method, minmaxGasDist, takes two inputs, an array of integers representing the positions of existing gas stations, and an integer k, which is the number of additional stations we can place. Inside this method, we define a helper function called canPlaceStations. This function checks if a given maximum distance is feasible by simulating the placement of stations. It iterates through the gaps between consecutive stations, calculating how many additional stations would be needed to ensure no gap exceeds the given maximum distance. If the total count of extra stations exceeds k, the function returns false, otherwise, it returns true. This helper function is key for evaluating whether a candidate distance is valid. After defining the helper function, we proceed to set up a binary search to find the minimum maximum distance. We initialize left to 0 and right to the largest possible gap, which is the distance between the first and last stations. We also define a small precision threshold, epsilon, to determine when to stop the search. The binary search loop continues until the difference between left and right is smaller than epsilon. For each iteration, we calculate the midpoint and use the canPlaceStations function to check if the midpoint is a feasible maximum distance. If it is, we narrow the search range by setting right to mid, otherwise, we set left to mid. Finally, once the loop terminates, we return left as the smallest maximum distance that satisfies the problem constraints. To solve the problem of minimizing the maximum distance between gas stations, we start by initializing our binary search range. The variable left is set to 0, representing the smallest possible distance, while right is set to 4, which is the distance between the first and the last station in the input. We also define a very small value, epsilon, to determine when the binary search has converged. In the first iteration, we calculate the midpoint of our range, mid equals 2.0, and use a helper function, can_place_stations, to check if we can place the additional two stations such that no gap exceeds this value. Looking at the gaps between consecutive stations, all are 1, which is less than 2.0. Since no additional stations are needed, the function returns true, and we adjust our range by setting right to mid, narrowing it to 0, 2.0. In the next step of the binary search, we calculate the new midpoint, mid equals 1.0, and again call can_place_stations to check if the maximum gap can be reduced to this value. As before, we look at the gaps between the stations, all of which are exactly 1. Since the gaps are equal to 1.0, no additional stations are required, and the function returns true. This allows us to further narrow the range by setting right equals mid, which now becomes 0, 1.0. At this point, we continue refining the range until the difference between left and right is less than or equal to epsilon. Once the binary search converges, the smallest maximum distance we find is 1.0, which is returned as the output. Now, let's examine a scenario where the gaps between stations are larger. With the input stations equals 1, 5, 10, and k equals 3, we begin by setting left equals 0, right equals 9, and epsilon equals 1e6. In the first iteration, we calculate mid equals 4.5 and check if we can place 3 additional stations to cap the maximum gap at this value. The first gap, 4, divided by 4.5 results in approximately 0.88, so no extra stations are needed here. The second gap, 5, divided by 4.5 results in approximately 1.11, which means we need 1 extra station. Since the total extra stations needed is 1, which is less than or equal to k, the function returns true, and we update right equals mid, reducing the range to 0, 4.5. Next, we calculate a new midpoint, mid equals 2.25, and call can_place_stations to check this maximum gap. For the first gap of 4, dividing by 2.25 results in approximately 1.77, so we need 1 extra station. For the second gap of 5, dividing by 2.25 results in approximately 2.22, so we need 2 additional stations. This gives a total of 3 extra stations, which matches k. Since the solution is valid, we update right equals mid, narrowing the range to 0, 2.25. We continue this process, refining the range through binary search until the difference between left and right is less than epsilon. The smallest maximum distance found is 2.25, which is returned as the result. Finally, let's consider an edge case where the stations are far apart. The input stations equals 1, 100, and k equals 10 gives us a large initial range, with left equals 0 and right equals 99. We perform binary search as outlined earlier, repeatedly computing the midpoint and checking if the additional 10 stations can sufficiently reduce the maximum gap. Through multiple iterations, the range is narrowed until right-left is less than or equal to epsilon. The smallest maximum distance that satisfies the conditions is found to be approximately 9.090909, and this value is returned as the output. To analyze the time complexity of our solution, we need to consider two main components, the binary search process and the helper function, can_place_stations. First, let's look at the binary search. Here, we're searching for the minimum possible maximum distance between gas stations. The range of this search is determined by the maximum distance between the first and last stations, denoted as d. With each iteration, binary search reduces the search space by half, and this continues until the difference between left and right is smaller than a very small threshold, epsilon, which is typically set to 1 times 10 to the power of -6. This gives us a logarithmic number of iterations, specifically O log d/epsilon. Next, in each iteration of the binary search, we call the helper function can_place_stations, which iterates through all the gaps between consecutive stations. If there are n stations, this operation takes n time. Combining these two components, the total time complexity is the product of binary search iterations and the time taken per iteration, resulting in n*log d/epsilon. Now, let's break this down further. The variables in our time complexity include n, the number of stations, d, the maximum distance between the first and last stations, and epsilon, the precision threshold, which is a constant. Moving on to space complexity, the solution is highly efficient in terms of memory usage. The binary search process only uses a few variables, left, right, mid, and epsilon, all of which consume O1 space. Similarly, the helper function can_place_stations does not require any additional data structures. It operates directly on the input stations array, which is passed by reference, and only uses a few loop variables. Therefore, the auxiliary space required by this algorithm is also O1. Altogether, the space complexity of the entire solution is constant. Compared to a brute force approach, which might involve storing additional data or performing unnecessary computations, the optimized approach is far more space efficient. Let's take a closer look at why the binary search method is so much better than a brute force approach. In a brute force solution, we would test every possible maximum distance within the range of d to determine feasibility. If the precision threshold, epsilon, is very small, say 1 times 10 to the power of -6, this would result in roughly d/epsilon iterations. When combined with the n time required to scan through station gaps, the overall time complexity of brute force becomes n*d/epsilon. This is significantly worse than the binary search, which only requires n*log d/epsilon time. The optimized approach is grounded in the monotonic nature of the problem. As the maximum allowed distance decreases, the number of additional stations required increases. This monotonicity allows binary search to efficiently narrow down the solution space while maintaining correctness. Additionally, if we analyze best and worst cases, the time complexity remains logarithmic in d/epsilon. In the best case, convergence happens faster if the optimal distance lies near the midpoint of the range. In the worst case, the maximum possible iterations are proportional to log d/epsilon, but even then, the algorithm scans the n stations in linear time per iteration. Regardless of whether we are in the best or worst case, the overall time complexity of the solution remains n*log d/epsilon. This is a significant improvement over brute force methods, especially for large input sizes or when high precision is required. To conclude, the binary search approach strikes an excellent balance between precision, determined by epsilon, and computational efficiency. It achieves logarithmic convergence with respect to the search space and operates in constant space, with a total space complexity of 1. These characteristics make it a highly efficient and scalable solution for minimizing the maximum distance between gas stations. This optimized approach is particularly well-suited for use cases involving numerous stations or stringent precision requirements, where brute force would simply be impractical. When solving this problem, there are several common mistakes to be aware of. First, many candidates overcomplicate the brute force approach. Remember, the brute force solution is supposed to be simple and serve as a foundation for optimizations later. Trying to optimize too early can lead to unnecessary complexity and wasted time. Interviewers often prefer to see a clear, iterative approach to problem solving, starting with a basic working solution. Next, incorrect handling of edge cases is another frequent pitfall. For instance, failing to consider scenarios like having only one gas station or evenly spaced stations can lead to incorrect outputs. A classic example is when there's just one road segment of length 100. Here, the maximum distance is clearly 100, not 0. Finally, misinterpreting the problem statement can cause significant issues. For example, confusing the goal of minimizing the maximum distance with minimizing the average distance can derail your solution entirely. It's essential to carefully read and understand the problem constraints and objectives to avoid this mistake. Another area where candidates often struggle is with numerical precision issues. Since this problem involves floating point calculations, directly comparing values can result in subtle errors. Instead, use a small threshold like 1 epsilon 6 to compare values for equality. This ensures your solution is robust against precision-related edge cases. Additionally, binary search implementation is a common source of inefficiency. Errors like incorrectly calculating the midpoint or improperly updating search bounds can lead to infinite loops or incorrect results. To avoid these pitfalls, it's crucial to validate your binary search logic with small, manageable test cases. This step helps ensure that your implementation is both correct and efficient, especially under edge conditions. Now, let's talk about some insights that can help you navigate this problem effectively in an interview setting. A key takeaway is that this problem often requires a combination of brute force and binary search techniques. Begin with a basic solution to establish clarity, then refine it using greedy or binary search methods to optimize performance. It's also important to stay focused on minimizing the maximum distance, as this is the critical metric driving the problem. This often means breaking the problem into smaller subproblems or using mathematical reasoning to guide your decisions. Another key aspect interviewers evaluate is your ability to balance theoretical knowledge with practical coding skills. For example, understanding the mechanics of binary search is important, but so is implementing it correctly. Lastly, communication is vital. Clearly explain your thought process, justify your approach, and actively validate edge cases with the interviewer. This demonstrates not only your technical skills but also your collaborative problem-solving ability. This problem is closely related to several other well-known problems on LeetCode, which can help you build a stronger intuition for the underlying concepts. For example, LeetCode 410, split array largest sum, involves minimizing the largest chunk sum and is often solved using binary search. Similarly, LeetCode 875, Cocoa eating bananas, focuses on minimizing the rate of consumption under constraints, again using binary search principles. Another related problem is LeetCode 1011, capacity to ship packages within D-days, which optimizes the maximum load capacity. All of these problems share the same core idea of minimizing a maximum metric, and they rely on efficient techniques like binary search to find the solution. By practicing these, you'll gain a deeper understanding of how to approach optimization problems with constraints. Finally, let's discuss alternative approaches to solving this problem. One intuitive method is the greedy approach, where you place gas stations in a way that reduces the largest gap iteratively. While this method is fast to implement, it doesn't always guarantee the optimal solution, as it may overlook better global placements. A more efficient and reliable method is binary search on the answer space. Here, you treat the maximum allowable distance as the search range and iteratively narrow it down by checking the feasibility of your midpoint distance. This approach is highly efficient, with a time complexity of n log max distance, but it does require careful implementation of the feasibility check. Lastly, there's a dynamic programming approach, which involves partitioning the road into segments to calculate the minimum-maximum distance. Although this method is a good exercise for understanding state transitions, it's usually slower and more complex than binary search, with a quadratic time complexity. Each of these approaches has its trade-offs, so choose based on the specific requirements and constraints of the problem. Thank you for joining me today. To summarize, we tackled an interesting optimization problem using binary search and greedy validation. We reviewed its time complexity, key insights, and practical applications. Remember, problems like this are excellent for sharpening your algorithmic thinking. Make sure to practice similar problems to solidify your understanding. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!